All right, guys, what we're going to do now is using electromagnetism to make what's called a rail gun. Okay, so what I want you to imagine right here is we have these two conducting rails. Okay, we're going to first assume that they have no resistance. They're like perfect wires, but they are very, very good conductors. And then what we're going to do on the other end here of the rails is we're actually going to connect them with a resistor and a battery with EMF of epsilon. So we have not a complete circuit yet, but you can see the battery here, the resistor, and then it's touching each of the rails. And then the next thing I'm going to do is I'm actually going to go ahead and complete the circuit with, let's just lay a metal bar across the two rails, right? So what I have inside of this right here is a complete circuit. I've got this metal bar sitting across the rails to complete the circuit. You can see then that I would have current flowing in this direction. So this would be current flowing in this direction, going down the bar and then back into the battery like that. Okay, and this is great. I have a complete circuit. So now what I want to do is I want to fill the interior space with a uniform magnetic field. So that's what I have here. I have a uniform magnetic field into the page, and if my rails are really, really long, then I need to extend this magnetic field all the way out here, and I can do this, make these rails as long as I want. Because what's going to happen next, if you think about the charges inside of this rod, well, if I have current, then this rod or this bar sitting on top of the rails is like a current carrying wire in a magnetic field. And you know that a current carrying wire in a magnetic field feels a force of Bill, right? Bi times the length being this distance between the rails right here, or the length of the bar between the rails. So we're going to feel a force on this bar, and if this bar is free to slide along the rails while still connecting the rails and completing a circuit, then we can get this rod or this bar to accelerate to really, really high speeds. If you have really long bars and a nice high magnetic field, you see that we could really get a large force for a long time on this bar. So the next thing I want to do is I want to consider, okay, what direction is the force going to be? Well, the current is down, the magnetic field is into the page. So in using the right-hand rule, pointing your hand down in the direction of the current, curling your fingers into the page, you'll notice that your thumb is pointing to the right. Your thumb is pointing to the right, so that means that this bar would start accelerating to the right. And we could, of course, we could figure out what the acceleration of that bar is. We would say that the Bil, B-I-L, the force acting on that bar is equal to ma. So we could calculate the acceleration of this bar, and really there'd be no end to this. You could make the rails as long as you want. Even as this bar starts to move to the right, it's still going to complete the circuit, and there's still going to be a clockwise current on this circuit the entire time, as long as this bar is completing the circuit and connecting the two rails. So we could really get this thing to accelerate to really, really high rates, and it could be used for lots of different things. One application is what's called the railgun, which is you would use this thing as a dangerous projectile. Have a long uniform magnetic field with these long rails that you could accelerate this bar just by putting a voltage between the rails, and that's pretty neat. What I'd like to talk about now is what's also going to be happening inside of the bar, which makes the railgun a little bit less practical when you really think about what's happening inside of the bar. Also consider that we said, these rails are perfect conductors. They offer no resistance, and of course we know that's not true, and the longer you make these rails, the more resistance they are going to add. So it definitely cuts into the practicality of the railgun, but it is doable. So let's talk about what's happening inside of the bar itself, the rod that you've put over the rails. What I want you to do is I want you to imagine just a bar, okay? And I'm going to put that bar in a magnetic field. Again, a uniform magnetic field. I'll do it into the page, okay? And imagine then that this bar is moving to the right. You just have some means of dragging this bar across the page to the right. Okay, so that's the velocity of this bar. And this bar, while it's a neutral conductor, it still has charges inside, right? So what I'd like to do is I'd like to kind of just zoom in on that bar. Okay, so I'll get an image here of what's happening inside of that bar. As this bar moves to the right, I want you to do a right-hand rule on the charges inside of this bar. Okay, so again, we're gonna do a QV cross B, where V is to the right, so I'm putting my hand to the right. B is into the page, so I'm curling my fingers into the page, and you notice that my thumb is pointing up. Well, that means that positive charges are going to want to move to the top. So positive charges are going to start to accumulate on this bar at the top. But if I use either the left-hand rule or I flip my right-hand rule by 180 degrees, I could also say that minus charges are going to start moving to the bottom. Okay, so this is just a bar, not connected to a battery. It's just, it's moving. There's something, maybe I'm dragging it across with a rope or something. So I'm finding a way to pull it across this uniform magnetic field, and you'll notice that I've made some almost like a capacitor here. I mean, it's not filled with insulator, so it doesn't have any dielectric material inside, but I have managed to separate the positive and the negative charges on this conductor. And that's created what is like a capacitor. It's also created an electric field between the charges. So now inside of my conductor, I have an electric field. You know that doesn't happen in a static situation, right? In electrostatics, the conductor does not have an electric field inside of it, okay? But this is not a static situation. We are moving the bar and we are forcing the charges to separate, okay? So what we've done is we have effectively created an electric field inside of the bar where the force on all the charges inside of the bar due to electricity is Q times the electric field. So let's consider one charge Q, okay, like this guy right here. This guy right here, this charge Q, how is he remaining here in this position? Why does he not go back to the center and neutralize? There's an electric field that wants him to come back to the center and neutralize, but there's also a magnetic field and a magnetic force that is forcing him up to the top. And over time, these charges are going to reach equilibrium, right? As I move this bar in the magnetic field, the charges are going to separate, and they're going to look like a capacitor in equilibrium. I've got positive charges on the top, negative charges on the bottom, so the force on each charge would be both an electric force and a magnetic force, and they've reached an equilibrium where those charges remain at the extreme ends of the bar. Okay, so what I can say then is if I cancel out the charge on each side, then the electric field that I've created is equal to the velocity of the bar times the magnetic field. So again, this is the electric field that I created by moving the bar in the magnetic field. Okay. But if you remember, when you have a capacitor, you remember that voltage, right? Voltage is ED. It's the electric field times the separation of the plates. That's what we said for a capacitor. That's what we said for parallel plates. The voltage across the plates is equal to the electric field times the distance between the plates. You can see this on your equation sheet. The equation looks like this. It actually is written as delta V over R, I believe. That's what it looks like on your equation sheet. But again, this is what we said for a capacitor or parallel plates. That the voltage across the plates is equal to the electric field times the separation distance. Okay? So what I'm going to do then is I'm going to say, well, then the voltage that I've created on this bar, I now have a voltage. If I were to measure with a voltmeter, put the positive lead here and the negative lead here, I now have a voltage on this conducting bar. And that voltage would be equal to the electric field times the separation distance. Well, separation distance would just be the length of the bar between the rails, right? That would just be our length of the bar between, I'm sorry, the length of the bar in the magnetic field. Okay, great. We also know the electric field in terms of the magnetic field and the velocity of our bar. So I'm going to go ahead and substitute VB in for the electric field. And then for the separation distance between charges, well, that's just going to be the length of the bar in the field. And that is to say that the epsilon, the new voltage that I have created, is, and I like to write it this way, BLV, just because I have it as a mnemonic. Epsilon is kind of like boulevard, but it's magnetic field times the length of the rod or the bar times the velocity at which you move it. And this is what is called EMF, the electromotive force. Okay, so what I'm doing right now is I am looking at the creation of an EMF, the creation of a voltage on a moving bar in a uniform magnetic field. Now, this concept of force is pretty simple to see when it's just a single bar. We're going to get into Faraday's law next, which is going to give us a better explanation of what is happening in this situation, and it's also going to be more useful for different geometries. I do this first. I always do electromotive force first because it's easy to see for this rod why we get a separation of charges and why there would be a voltage on this bar. But when we get to a little bit more complicated geometries, it's much more difficult to think about it in terms of force, and we're gonna use Faraday's law instead. Okay. But right now with the single bar, it's not too bad to think about force. I think it makes sense. I think it gives us a good foundation to build Faraday's law and electromagnetic induction. Okay. The next thing I could do with this bar, which is pretty simple, is just like the railgun, I could very simply connect this moving bar to rails, and I don't need a battery now. If I were just dragging this rod along with a string or something, I could maybe just put a resistor on the back end here. So now the moving rod is actually creating my EMF or my voltage, and the moving rod is going to want to make current move in this direction. Okay, and for example, we could actually measure the amount of current in this closed circuit. The current would just be, well, if I go to the resistor and I measure the voltage on the resistor, that's going to be the same as the EMF on the rod. So I would take epsilon over R, but we said again that epsilon on the rod here is BOLV. So the current in this system is just BOLV over R. And as I continue to move this thing to the right, it would continue generating an EMF, and I could continuously get this counterclockwise current. Okay, but I do want to take you back to the railgun. I want you to think about, well, if the battery was forcing the bar to move to the right because of the current that the battery generated, but when the bar moves to the right, we see that the EMF created inside of the bar is actually going to make current go the opposite direction in a counterclockwise fashion. That is, there's a limit to how fast we can get this railgun moving. Because eventually when you reach a high enough speed, the EMF created inside of the bar is going to be greater than the EMF of the battery. And at that point, you're no longer going to speed up. So there's definitely a limit to the railgun. The practicality of it is in question because we don't have perfectly conducting rails, perfectly conducting bar. There's definitely going to be some resistance there, especially when you get to really long lengths. This voltage has to be high enough so that it can overcome the voltage that we induce on the rod itself. Okay, but I like to do those two together, the railgun and then the electromagnetic induction. Again, this is using force to explain why there is an EMF generated. The next thing we're going to do is Faraday's law, which is going to allow us to do more complicated geometries. Okay.